Far out in the dark and chilly part of our solar system, there's a giant. This giant is not just any planet, it is a world that has fascinated astronomers and scientists for centuries. Its distance from the sun makes it one of the most mysterious and least understood planets in our solar system. A blue world, full of mystery. Neptune's deep blue color is unlike any other planet in our solar system, giving it an almost otherworldly appearance. This striking hue has led to many questions and theories about what lies beneath its thick atmosphere. This is Neptune, the 8th planet from the Sun. Positioned so far away it takes sunlight over 4 hours to reach Neptune. This distance places Neptune in a region of space where temperatures plummet and the environment is incredibly harsh. It's 4 times wider than Earth, a place of icy clouds and superfast winds. These winds can reach speeds of up to 1,200 miles per hour, making them the fastest in our solar system. The atmosphere is composed mainly of hydrogen, helium, and methane, creating a dynamic and turbulent environment. Neptune shows us how powerful and beautiful our universe is. Its majestic presence and the violent storms that rage across its surface are a testament to the raw power of nature. The planet's rotation period is about 16 hours, which means it completes a full spin faster than Earth. Even with strong telescopes, Neptune looks like a small blue dot. This tiny speck in the vastness of space is a reminder of how much there is still to learn about our solar system. Despite its distance, the Hubble Space Telescope and other advanced instruments have provided us with valuable insights into Neptune's characteristics. Because it's so far away, it's hard to study. The immense distance poses significant challenges for scientists trying to gather data. Space missions to Neptune are rare, and the information we have comes from a combination of telescopic observations and the Voyager 2 flyby in 1989. But what we have learned shows us a truly strange world. Neptune's atmosphere is filled with complex weather patterns, including massive storms that can last for years. The Great Dark Spot, a storm similar to Jupiter's Great Red Spot, was one such feature observed by Voyager 2, a world that is both beautiful and dangerous. The swirling storms and high-speed winds create a hostile environment, yet there is a certain beauty in the chaos. The planet's deep blue color adds to its allure, making it a captivating subject for study. Neptune's bright blue color comes from methane gas in its air. This methane absorbs red light from the sun, leaving the blue light to be reflected back into space. This process gives Neptune its distinctive and mesmerizing appearance. This gas soaks up red light from the sun. The interaction between sunlight and Neptune's atmosphere is a complex dance of absorption and reflection, resulting in the planet's unique coloration. We only see the blue light that bounces back. This phenomenon is similar to why Earth's sky appears blue, but on Neptune, the effect is much more pronounced due to the higher concentration of methane. This gives Neptune its special, almost ghostly look. The planet's ethereal glow has inspired many to wonder about the secrets it holds and what other mysteries might be hidden in the depths of its atmosphere. Neptune isn't alone way out there. It is accompanied by a collection of moons, each with its own unique characteristics and stories to tell. It has 14 moons that we know of, going around it. Triton, the largest of these moons, is particularly interesting because it orbits Neptune in the opposite direction of the planet's rotation, suggesting it may have been captured by Neptune's gravity long ago. Each moon has its own secrets, just waiting for us to discover them. From the icy surface of Triton to the smaller rocky moons, Neptune's satellite system is a treasure trove of information that could help us understand more about the formation and evolution of our solar system. Neptune is an ice giant, just like Uranus. These two planets are unique in our solar system, and their formation and composition set them apart from the other planets. Understanding Neptune's formation helps us grasp the broader processes that shaped our solar system. This makes them different from the gas giants, Jupiter and Saturn. While Jupiter and Saturn are primarily composed of hydrogen and helium, Neptune and Uranus have a different story to tell. Their unique characteristics are a result of their distinct formation processes and the materials they accumulated. But what does it mean to be an ice giant? Unlike gas giants, ice giants have a significant amount of elements heavier than hydrogen and helium. These elements include water, ammonia, and methane, which exist in various states, including ices, under the conditions found on these distant planets. A long time ago, our solar system was a messy place. It was a chaotic environment filled with swirling gas and dust, remnants from the formation of the sun. This primordial cloud, known as the solar nebula, was the birthplace of all the planets, including Neptune. It was a swirling cloud of gas and dust left over from when the sun was born. Within this protoplanetary disk, particles began to collide and stick together, forming larger and larger clumps. These clumps eventually became the building blocks of planets. Inside this cloud, tiny bits bumped into each other and stuck together. Over time, these collisions and accretions led to the formation of planetesimals, the precursors to planets. Gravity played a crucial role in pulling these materials together, allowing them to grow in size and mass. Gravity pulled in more stuff, and over millions of years the planets formed. This process, known as accretion, was responsible for the creation of all the planets in our solar system. The inner planets, like Earth and Mars, formed from rocky materials, while the outer planets, including Neptune, formed from a mix of ices and gases. Jupiter and Saturn, closer to the Sun, ate up lots of hydrogen and helium. These light gases were abundant in the inner regions of the solar nebula, allowing Jupiter and Saturn to grow massive and develop thick, gaseous atmospheres. These light gases made their huge, puffy atmospheres. The immense gravity of these gas giants helped them retain these light elements, resulting in their characteristic large and dense atmospheres. Neptune and Uranus, further away, formed differently. In the colder outer regions of the solar nebula, the conditions were not as favorable for accumulating large amounts of hydrogen and helium. Instead, these planets gathered more ices and heavier elements. They also collected hydrogen and helium. However, the amounts were much smaller compared to Jupiter and Saturn. The lower temperatures in the outer solar system allowed for the formation of ices, which became a significant component of Neptune and Uranus. But because they were so far from the sun, other things like water, methane, and ammonia froze into icy bits. These ices, along with rocky materials, contributed to the unique composition of Neptune and Uranus, distinguishing them from the gas giants. These icy bits, along with rock, make up a big part of Neptune. The presence of these ices gives Neptune its distinct blue color and contributes to its overall structure and density. That's why Neptune and Uranus are called ice giants. Their formation and composition are dominated by ices and heavier elements, setting them apart from the gas giants. They're made of different stuff than the gas giants. This difference in composition is a direct result of their formation environments and the materials available in those regions of the solar nebula. They are worlds shaped by the cold. The frigid conditions of the outer solar system played a crucial role in the formation of Neptune and Uranus, making them the fascinating ice giants we study today. Neptune has the wildest weather in the solar system. This distant, icy giant is a world of extremes, where the atmosphere is a chaotic mix of hydrogen, helium, and methane. The planet's vibrant blue color is due to the methane in its atmosphere, which absorbs red light and reflects blue. But beneath this serene blue exterior lies a world of violent weather patterns and extreme conditions. Winds blow across the planet faster than the speed of sound. These winds can reach speeds of up to 2,100 kilometers per hour, making them the fastest in the solar system. To put that into perspective, the speed of sound on Earth is about 1,235 kilometers per hour. So the winds on Neptune are almost twice as fast as the speed of sound on our planet. Imagine a hurricane, but instead of wind and rain, there are clouds of frozen methane. These storms are not only incredibly fast, but also extremely cold. The temperature on Neptune can drop to a frigid minus 214 degrees Celsius. This means that the methane in the atmosphere can freeze, creating icy clouds that swirl around the planet at breakneck speeds. The fastest winds ever measured on any planet were on Neptune. These winds are driven by the planet's rapid rotation, which takes just 16 hours to complete a full spin. This rapid rotation creates powerful jet streams that whip around the planet, driving the high-speed winds and creating the extreme weather conditions we see. These winds can blow up to 2,100 kilometers per hour. That's faster than the most powerful hurricanes on Earth, which can reach speeds of up to 350 kilometers per hour. The sheer force of these winds is enough to tear apart anything in their path, creating a truly hostile environment. That's more than 6 times faster than the strongest hurricanes on Earth. The comparison between Neptune's storms and Earth's hurricanes highlights just how extreme the weather on this distant planet can be. While hurricanes on Earth can cause widespread destruction, the storms on Neptune are on a completely different level, with winds that are far more powerful and temperatures that are much colder. These super-fast winds create giant storms. These storms can last for months or even years, swirling around the planet and creating massive dark spots that can be seen from space. These dark spots are similar to the Great Red Spot on Jupiter, but they are much more transient, appearing and disappearing over relatively short periods of time. The most famous was the Great Dark Spot, a swirling storm bigger than Earth. Discovered by the Voyager 2 spacecraft in 1989, this massive storm was a prominent feature on Neptune's surface. It was similar in size to Earth, and had winds that reached speeds of up to 2,400 kilometers per hour. The Great Dark Spot was a testament to the extreme weather conditions on Neptune. Voyager 2 discovered this storm in 1989. The spacecraft's flyby provided the first close-up images of Neptune, revealing the planet's dynamic atmosphere in the presence of the Great Dark Spot. This discovery was a major milestone in our understanding of the outer planets and their weather patterns, but when the Hubble Space Telescope looked for it in 1994, it was gone. The disappearance of the Great Dark Spot was a mystery to scientists. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms seem to be much more fleeting. This raises questions about the mechanisms driving these storms and their lifespans. Neptune's storms are a puzzle. Despite the planet's distance from the Sun and the limited amount of solar energy it receives, it still manages to generate some of the most powerful storms in the solar system. This has led scientists to investigate other sources of energy that could be driving these extreme weather patterns. The planet doesn't get much energy from the Sun. In fact, Neptune receives only about 1/900th of the solar energy that Earth does. This means that the Sun's energy alone cannot account for the planet's violent weather. So where does the energy come from? So what makes these fierce winds? Scientists believe that the answer lies within the planet itself. Neptune is thought to have a significant amount of internal heat, which is left over from its formation. This heat is slowly released over time, driving the powerful winds and storms that we see on the planet's surface. Scientists think heat inside Neptune, left over from when it formed, might be the cause. This internal heat, combined with the planet's rapid rotation and unique atmospheric composition, creates the perfect conditions for extreme weather. As we continue to study Neptune, we hope to uncover more about the mysteries of this stormy paradise and the forces that drive its wild weather. Finding Neptune is a great story of math and careful watching. It was the first planet discovered not by accident, but by using math. In the early 1800s, astronomers noticed something odd about Uranus's path. It wasn't moving the way Newton's law of gravity said it should. Something we couldn't see was pulling on it. Two mathematicians, Urbain Le Verrier in France and John Adams in England, both figured out the answer. There had to be another hidden planet past Uranus pulling on it with its gravity. Le Verrier sent his calculations to Johann Galle at the Berlin Observatory. Galle pointed his telescope where the math said to look, and on September 23, 1846 he found Neptune. Finding Neptune surprised everyone in science. It showed how powerful Newton's physics was and helped us understand the solar system better. When we think of rings, we think of Saturn. But Neptune also has rings, though they're much fainter and harder to see. These rings aren't as big as Saturn's, but they're still beautiful. Neptune's rings are made of ice particles and dust. Scientists believe they're pretty new, much younger than Neptune itself. One idea is that they formed from the leftovers of crashes between Neptune's moons. The rings aren't smooth but lumpy, with arcs of thicker material. One reason for these arcs might be Galatea, one of Neptune's moons. Galatea's gravity might be keeping the ring material together so it doesn't spread out. Neptune's rings remind us that even in the darkest parts of our solar system, there are amazing and beautiful things.